see it properly? Where can't you see? Was it over here? Ooh, I like this. Who did that? You can probably see it so like diagonal, you know? Oh, it's recording. Hey guys! Record like 5 minutes and nothing.
I got the battery and the stage. Well, all these I did not use it. You started moving yet? I gotta print it. Yeah. Oh my god, why does he sound like this to us? How many would you drop? Yeah, this one. For what?
You can't drop by 4 because of the chance.
Alan is doing this.
You get the plain one? You okay there?
Yeah.
Are you recording?
Yours like that. Start with social media.
Oh my god. Oh no.
Monster.
I'm just zooming in. I'm just slowly zooming in on Sarah.
It's recording too.
I know.
It's 20 degrees from the right? So then I did 20 degrees.
We're telling you. Your arms in the frame. Excellent.
They suck.
They suck.
They suck.
They suck.
Are you gonna finish your
Really? Why?
Then on the test, she bumps it up like 3
I was gonna go this way.
Did you check?
Yo, I'm gonna end up solving this Jinx spirit.
I feel like I'm in the wrong seat. I should be in this seat. I should be here.
Whatever I want. Yeah, I know.
Because I separated it into, I got the Cartesian equation and I made a triangle. So we did the first one, right? So the X and then like the 40-degree bearing.
Got a highlighter mark?
Oh, I'm talking about the
There's no one. It goes 40, then 90, so that's 40 to 90.
It's been recording for like 3 minutes already.
Okay. We'll just tell him to fast forward.
Fast forward the last 3 minutes.
That doesn't work. That doesn't work. It's 3 minutes into the video and he just tells us when.
We ended off last class talking about Henry's law, the idea that if we increase the partial pressure of a gas at the surface of a liquid, we increase the gas solubility. Electrolytic solutions are the ones that we're going to be primarily concerned about in this section.
All right.
Electrolytic solutions can be 3 types. Most of the ones we're going to be looking at are strong electrolytes. In other words, almost all salts generate strong electrolytic solutions. Remember, salt is not sodium chloride. Salt is a general name for just about all ionic compounds. If it's ionic, it's a salt. Okay? Well, electrolytes, yeah, you've heard of Gatorade, right? So, what that's about was in the 1960s, the University of Florida was having problems with their athletes during summer training for their football team. The Florida Gators, that's where Gatorade came from. What happens in the 60s, when they were doing their summer training, the athletes would be suffering from severe cramps and dehydration. What's happening is that as you're sweating, if you ever had the unfortunate accident of tasting sweat, it's very salty.
Ew.
Right? Yeah, I'm into it. You know what? Sweat drips or whatever, everybody's tasted salt, or for that matter, tears are the same thing. So they're very salty because they're full of electrolytes, specifically sodium and potassium. And you guys have studied that class over there. How do muscles contract? They contract because of the sodium ion potassium pump and how these ions are pumped across the membrane of the muscle tissue. If you sweat too much, you throw off that sodium-potassium balance, causing cramps. So that pump seizes and the muscles cramp. So what happens is in the 60s, the Florida training staff were trying to figure out ways to help alleviate the cramping and dehydration problems, so they invented Gatorade. So they would take this orange Tang, like the astronauts drinking an orange powder drink, and they would add extra sodium and potassium to it. So therefore they'd be replacing the electrolytes as they were exercising. That's how Gatorade was formed. Okay. Now what ended up happening is that it worked really well, but the problem is the original Gatorade almost had two different tastes. If you weren't working out and you tasted it, it was extremely salty because you weren't doing anything with the sodium and potassium. They were just in your mouth, and so you would stimulate the salty part of your taste buds, and it would taste very salty. If you were exercising a lot, it wouldn't have that salty edge anymore because you were dissolving the electrolytes faster than the taste buds could pick them up. So you'd lose that salty taste. And since then, they realized they had $1 million business, and they added a ton of sugar to it and sold it to everybody else as an energy drink. And that's how the energy drink market started. So, but it's electrolytes. And what the true definition of an electrolyte is just any solution that's able to conduct electricity. And if you're able to conduct electricity, it's because you have these free-moving ions with Gatorade, it's sodium and potassium in particular. But any ionic compound will generate an electrolytic solution when dissolved. In other words, as the ion dissolves and breaks apart, we generate free-moving ions. We're able to conduct electricity. Weak electrolytic solutions would be things like your organic acids, organic bases, which don't generate a lot of ions. Okay? So the ability to conduct electricity is greatly reduced, so they're called weak electrolytes. And then if you have polar or dipole molecules that are dissolved in solution, or even LDF molecules dissolved in solution, because there's no ions generated, they're not able to conduct electricity, therefore they're non-electrolytic solutions. So that's all that is, just kind of talking about the three types. We're not going to get into it any more than that. These next few notes here about hydration energies and dielectric effect, I just want you to be aware of them. Again, not going to do much with it. Hydration energies, something we've talked about a lot last year, and most of this stuff, these hydration energies and dielectric effects, we did mention last year, so if you want more details about them, then just go to last year's notes.
Yeah. And in China, I started with my biochem physics.
Oh, last year.
Yeah, that's just. Was that chapter?
I honestly don't remember. No, you don't water the equation.
I don't really remember. Limiting me out.
Wow.
Wait, is it what?
Yeah.
Damn it, Martin.
You pulled a mark?
Yeah, I did.
Yeah, you pulled the Martin.
That's fine.
Okay. Hydration energies. What that is the energy involved as ions are surrounded by water molecules, often termed the solvation of ions. It's not the salvation of ions. We're not saving ions from eternal damnation or anything like that. It's solvation of ions. We're dissolving the ions. So if I take a look at, for example, sodium, the reason we know, we already talked about this, The reason why the crystal dissociates is as the sodium ion gets pulled out, it gets pulled out because of the attraction to oxygen's negative side of the molecule, right? We've got a negative side and a positive side because of the dipole nature of water molecules. So it completely surrounds the ion as it gets pulled out. So what we're looking at then, ions form easily due to the interaction between ion and water, called solvation, or for specifically hydration of ions. The positive end of the water attracts the anion, negative end attracts the cation. Remember, cations are the positive ions because cats are positively revolting. Okay, the only good cat's a dissected cat.
What about
Energy. What? What?
what?
I'm fine, Harry. The only good cat's a dissected cat.
That's pretty true, actually.
True.
When you if you get on into post-secondary and you do science, one of your basic, because in first year you generally take all sciences, doesn't matter what you want to specialize in. So you're going to have to take like anatomy and biology, right? You got to take it. That's what. But you get a cat, and you start dissecting the cat, and then 6 weeks later you hand your cat back in. So it's literally like your cat for 6 weeks.
Do I have to raise this cat up?
What they teach you, all you got to do is hold it kind of at the top of the head behind the ears, and then hold it just at the shoulders. And it's when you grab the jaw, no, you just twist.
Oh, you twist?
Oh, no, that's behind it. Like,
And if you get it, you kind of, it's nice and calm, you grab it like that, and you just go like that.
See me, I always go for the roadkill.
roadkill is much easier. Roadkill.
As long as you do it quickly and don't hesitate, anybody who hesitates, the cat kind of wails. But if you do it quickly, then it dies before you. I'm kidding. The cats are dead when you get it.
Oh, damn, that's disappointing.
I'm so
disappointed.
Oh my god!
Another dream broken.
Oh, another broken dream.
But seriously though,
I thought you got your
when you're speaking of electrolytes and Gatorade and that, when you're studying muscle contraction and ion conduction in muscle cells, you do have to pith frogs.
Yeah, you make them dance.
And what a pithing of a frog means, pithing, is it is a live frog that you do have to kill. And the idea is you need the muscle tissue as fresh as you can to be able to really look at conduction of the muscle tissue and how the muscle is able to conduct electric current in that. But again, you hold the frog in your hand, the legs dangling out in the head here, and you take, you've seen in dissecting kits those probes with the needle probes,
Yeah.
and you just take it behind the base of the skull, and you stick it into the foramen magnum, okay, and that goes through and hits the medulla.
I just want to record the reason.
You guys know what the foramen magnum is? It's the big opening where the spinal cord comes out of the skull,
Yeah.
right? And then if you go in through the foramen magnum, that pierces the medulla. Pierces the medulla. It pierces the medulla oblongata, and that instantly kills somebody. I mean, the frog.
Oh, okay.
Just because all you need is like an 8-gauge needle and walk in behind along the hairline and go through, and you're dead before you bleed. So that's one way I can kill somebody without leaving a mark. I mean, I'm kidding.
He's not.
But that's called pithing a frog, and you do have to. When you go to that class over there, just ask Miss Wakeland about pithing frogs. Okay, because again, same idea. If you don't get it exact, then the frog actually screams. What? Oh yeah,
Tongue flies out.
It's like a parrot.
So you're in the lab and all you hear, oh, that one missed. Oh, you missed. Okay, no sound? Got it. Nailed it. So, how did we get on this topic? Anyway.
How do we get here?
Oh yeah, the cat ions. I knew there was some reason. But anyway, energy released due to dipole ion interaction is the hydration energy. So what we can do is, as the ion gets pulled apart, dissolving is exothermic. So we can take a look at the energies involved in dissolving. And that's when we're looking at hydration energies, that's what we're looking at. We're looking at as the ion gets pulled out of the crystal, the negative poles of the water molecule will surround it. And the same idea here with this, with the chlorine, if it gets pulled out, okay, then it's just going to be surrounded by the positive aspects of the water molecule. Okay, so that's the hydration energy. It's the energy of the crystal dissociating. Looking at dielectric effect, dielectric, water molecules, dipole, positive and negative side. So the dielectric effect is oppositely charged ions do not recombine due to the insulating effect of water molecules. And all that means is, if I take a look, as I said, you see the way here, this chlorine ion is getting completely surrounded by water molecules. So if it gets completely surrounded, okay, by the negative part, that's going to prevent this chlorine from going back into the crystal. It can't, because it's surrounded and insulated by all the water molecules. And the same effect will be for the positive ion. Again, because water is polar, so we're able to use the two sides. And it's going to completely surround it and insulate it to prevent it from recombining into the crystal. So the dielectric effect is what allows the ions to stay dissolved in the solution. Okay? The only way to get the crystal back, of course, is to do what? How can you get your crystal back?
Boil the water.
Boil away the water. Okay? So that's all that's talking about, is oppositely charged ions do not recombine due to the insulating effect of water molecules. Ionic substances dissolve faster in solvents with high dielectric constants. Water has one of the highest dielectric constants because it's a small molecule. It can form, it's dipole. It's also able to form hydrogen bonding. So water has a very high dielectric constant. That's why it's able to dissolve a lot of different ions. Okay? So that's all we're looking at. If you want a little bit more detail with that, again, check your notes. You can check for grade 11 or just read through the textbook. But I'm introducing the concept, so you've heard of what dielectric effect means, what you've heard what hydration energies mean. Any questions with that? Now we start to have some fun. Okay. First half of the chapter was equilibrium of gases. So our equilibrium constant was Ke. Second half of the chapter is going to be equilibrium of solutions. Remember that if a precipitate is present, that is now an equilibrium system, therefore can calculate an equilibrium constant. Because it's a solution, to separate it from the concept of gases, it's KSP, the solubility product constant. Okay? When we get into the acids and base chapters, we're going to have a KW, a Ka, and a Kb. And we'll deal with that when we get into acids and bases. So, slightly soluble salts. Make sure you know what that means. Remember, if it's slightly soluble, only a little bit of it will dissolve. Most of it will precipitate. So if it's slightly soluble, a little bit will dissolve, most will precipitate. It is an equilibrium condition, an equilibrium state, because as particles are dissolving into solutions, other ones are precipitating out at the same rate. So, if we've got an equilibrium expression, we can calculate an equilibrium, if we have a KSP, we can write an equilibrium expression. Value of K is determined by the concentration of ions. Let's take a look at that. So, if you remember from the first part, we always started our questions with what? What was the first thing we did in every question? Balanced chemical equation. We're going to do the same thing for the KSP, except a balanced chemical equation. We're going to write a net ionic equation. So a balanced ionic equation. This is the reaction we're looking at. Subscripts are very important. So make sure when you're texting, you text that to the person you're texting that subscripts are extremely important. Got to have the right subscript. Solid, because that's what we're adding to the solution. This will dissociate into two soluble ions. Based on the rules that you know from last part of the chapter, what's the KSP expression going to be? That's why subscripts are important. Hint, hint, hint. KSP would be equal to products over reactants. Concentrations of products over the concentration of the reactants. Absolutely. And your exponents become, your coefficients become the exponents, just like KE. So any coefficient you have becomes the exponent. However, there was one condition we put on that. Solids are not part of the KE expression. That same rule applies. So what's my KSP expression going to be?
AgCl.
Concentration of silver times the concentration of chlorine. Okay? Make sure you have the ionic charge, please. Okay? And watch your coefficients, because the coefficient becomes the exponent. Okay, so we don't put the solid in there. Solid concentration actually remains constant. That's why it's not included. So if you think about our system for a minute, if I've got a beaker, and in the bottom of my beaker I've got my precipitate, my solid, right? We're an equilibrium system, which means as we're dissolving into solution at the same rate we're precipitating out of solution. So if that's the case, the concentration of your solid remains constant. It is changing at the atomic level, but it's a dynamic situation. The solution is saturated, so it can't hold any more solute. But we are dissolving into solution at the same rate we're precipitating out. You can almost think of it as at a lineup at a club. Club's full, you got the doorman with the numbers. 2 people come out, I'll let 2 people in. 1 person come out, 1 person can go in. 5 people come out, 5 people go in. Okay? So the club itself, the population of the club remains constant. The net population of the club remains constant. So that's why your solid isn't included in the precipitate, or isn't included in the KSP expression. It is the solid concentration remains constant. Okay? All right. So, having said that, here's another example. Okay? So here's our ionic equation. And if we're going to write that, then what we've got is the KSP, concentration of iron, times the concentration of hydroxide cubed. Okay, just showing you that same idea. Coefficients become the exponents. Okay? Any questions with that? Just really quick. Don't copy it down. We'll just do this really quick together. So we'll do this really quick together. If I've got, that is my solid, my KSP expression is just going to be silver squared times chromate. Now, you are responsible for nomenclature from last year.
Oh, great.
Exactly. The nickel-camel ions, make sure you know them. Nickel-camel plus the 8-ite, hypo-ite per 8, as well as page 99 of the textbook last year had that table. Chromate, dichromate, manganate, oxalate, permanganate,
That's all I remember.
as well as all their charges. Acetate,
What's thio again?
Thiocyanate. Thio replaced by
chromate, dichromate, permanganate,
Oh, oxygen and sulfur?
Yeah, you're placing oxygen versus sulfur.
oxalate,
Cyanate. This is CNO. Wait, no.
Thiocyanate
SCN. SCN.
acetate,
Yeah.
and like be able to use thiocyanate, like thio, right? If we're using thio, we're replacing one of the oxygens with the sulfur, charge stays the same.
Okay.
Okay? So chromate, dichromate, permanganate, oxalate, acetate, as well as I said, all the nickel-camel ones, including per 8, ite, and hypolites. Okay? Can't think if there's any more that you want to write down. If anybody wants, come see me and I'll see if I can get a copy of the tape of that chart from page 99 of the grade 11 book. Okay, any questions? So yes, you are responsible for all those formulas.
I probably wrote it down somewhere in my notes. I don't even write on too many notes to look through.
So we take a look at this one then. Aluminum hydroxide. Okay, KSP is going to be aluminum times hydroxide cubed. And then iodate. Everybody remembers iodate? Okay, all of the halogens are the same. So very, very quickly, they're all based on nic-the-camel chlorate, right? ClO3 is -1, right? So if you're using any of the halogens, just replace it with the other halogens. So iodate is -1, bromate, -1, okay? Fluorate is the only other one. Okay, so yes, you are responsible for polyatomic ion nomenclature. All right. And then iodate obviously becomes that. Okay, any questions? Pretty straightforward. Any issues at all? Everybody good? Okay. So, let's take a look then at KSP. Do that.
Spy bot.
Oh, well, whatever.
Chemistry teacher by day, spy by night.
James Bond by name.
Here, hydrochloric acid.
Anyway, all right, sample problem number 1. Molar solubility of copper hydroxide. Now, over the last several years, out of all the units on the final exam, this is the one unit that for some reason people bomb. And I've been looking back over the last few years, what can I do differently, what information, what am I doing that's not getting through, all that, how can I get through? So this year I've looked at, well, I think the problem is, as I look back over the years, we're not understanding what the question's really asking. So what we're going to do for today is we got an hour, we're going to break down each question individually that we're looking at. What is it telling you? And it's something I've been focusing on, especially in the second semester, but even right from the beginning, I said, you guys have to understand your balanced chemical equation, or even your balanced ionic equation, gives you so much more information than we comprehend and understand. And if we can understand what that's telling us, it will make answering the questions not easier, but more logical. Okay? The problem is, let's just look at that question and read it for a second. The molar solubility of copper hydroxide is 3.2, whatever. What is the KSP for copper hydroxide? And the problem is, we're looking at that as a number that we have to plug into an equation. So I think what's happening is that people are looking at it and go, okay, where does that number fit in the equation I need to use? As opposed to, what is the number telling me? And once I understand what the number is telling me, then the equation becomes secondary. Okay? So if I'm looking at this, let's forget the question. Just look at the first sentence. What is the first sentence telling you? What does that mean in plain English? Forget the chemistry and what we have to do with it and figuring it out in the equation and where does it fit in my equation. What is that statement, that first sentence saying?
Yeah.
You.
Just debating whether I want to go up, but I figure they'll go away in a minute. What is that saying? What does that mean? Put it into plain English. What's that first sentence mean?
For every liter, that amount of copper hydroxide dissolves.
That's exactly what it means. In 1 liter, I'm going to be able to dissolve that many moles of copper hydroxide. Okay? So, now that it means that, as I said, if I've got a sample, doesn't matter how much I have. If it's a 1 liter, this much will dissolve. The rest is going to do what? What happens if I add 5 moles? The rest precipitates. So if I add 5 moles of copper hydroxide, only this much is going to be able to dissolve, so I'm going to be left with a whole bunch of copper hydroxide at the bottom of the container. But that's an equilibrium system. It's dynamic. Some of it's dissolving into solution, but at the same rates, the same amounts precipitating out. So anything more than this is going to collect at the bottom of the container. Okay? Kind of getting it. All right. Now let's deal with it. So what is the KSP? All right. Step number 1, write the ionic equation. Go ahead and do that. Once you write the ionic equation, write the KSP expression. I don't know why it's not doing it.
What's that?
Sorry?
What's that?
I'm trying to make this, you know, that shade come up so I can raise that up. I don't want to show the whole expression. I want you to work on it yourself. But it's not doing it for some reason now. Try this.
The more that's concentrations from 0.42 times 10 to the negative 7.
No long. All right, so we do the net ionic equation, and then we write the KSP expression. So we got that far, right? Everybody's okay? Oh, I know what I can do. Just so I want to raise it up, that's all. I'll do it this way Okay, that way we can see it at least. Have they messed them up? Good. Okay? Molar solubility is that. So we're at the ionic equation. So what's the KSP expression? All right. Now, looking at that information and nothing more, in order to calculate the KSP, I need to know what the concentration of copper is, and I need to know the concentration of hydroxide. Obviously. Based on the balanced ionic equation, what do I know? This is one thing I know.
So 2-1 ratio. No, yes.
Sorry, what do you think?
So 2-to-1 ratio.
Of what?
Hydroxide and copper.
There's a 2-to-1 ratio of hydroxide to copper. In other words, for every copper ion I produce, I generate 2 hydroxide ions. Does that help us in any way, though, right now?
No. Well.
What else? Well, no. It is a very important piece of information. But there's one more thing we need to do before we can get that far. What other information do I know?
You know, at least one concentration.
Do I know the copper concentration?
Yes.
Why?
That's all I got.
You know the molar solubility?
That is exactly it. Because again, let's go back. What does molar solubility mean? For every mole, or it means that for every single liter of this, I'm going to dissolve that many moles. Okay? I don't have a volume in my question. So because of that, you can assume 1 liter container. So that means I'm going to have this many moles dissolved. It's a concentration of copper.
Same thing.
Why?
Because it's the 1-to-1 ratio with the copper hydroxide.
For every mole of this that dissolves, I generate 1 mole of copper. Okay? And as I said, I think this is the connection we're not making with these balanced equations. And this is why these questions are becoming so difficult, because we're not We've got to get away from, I've got a number, where do I plug that into my equation? No, what do the numbers mean? So I do know, we're right, I do know that that's the copper concentration. Because, and again, I'll take a step back, this statement right here is saying that for every liter I have, I'm going to dissolve that many moles of copper hydroxide. But if I'm dissolving that many moles of copper hydroxide, I'll be generating the same number of moles of copper ions, because that's what dissolving means. If I'm going to dissolve my copper hydroxide, I'm going to generate copper and I'm going to generate hydroxide. That's what the dissolving means. Those are the free electrolytes. Okay? So because copper is 1-to-1 with copper hydroxide, for every mole of copper hydroxide I dissolve, I'm going to create 1 mole of copper ions. Okay? Now, Josh, what do we know? If I know the concentration of copper, what else do I know?
The concentration of hydroxide.
Why?
Because it's 2-to-1 ratio, so you just multiply.
Exactly. 2-to-1 ratio. For every mole of copper I generate, I'm going to create twice as many moles as hydroxide. So hydroxide ion concentration is that. Now, just as a bit of a heads up, don't freak out if you get numbers 10 to the negative 51, 10 to the negative 37, 10 to the negative 28. That just means it's slightly soluble. Only a little bit will dissolve. Okay? All right. Now we've got our hydroxide. Now we've got our copper. Plug it in, calculate your KSP, and your KSP is...
Okay, wait.
And I'll show you the first of the very common mistakes being made. Do your answer, see if you get that number.
13,
That's highlighted.
14, 15, 16, 19.
If you didn't get it the first time, I know exactly why you didn't. If you got it the second time, you found your mistake. But if you didn't get it the first time,
No, that's not it.
one of the most common.
That wasn't it.
That was it.
Put that in brackets. But like redo it all.
We write the ionic equation, and again, this kind of goes back to how I was talking about the equilibrium questions. We write the ionic equation, no problem. But then we got to go through a whole series of calculations to calculate the values in my equation. And then when we go to plug it into our KSP again, we forget we squared something. Or we didn't multiply by 2 to get the hydroxide ion concentration. What, not the most common, but the second most common mistake made in KSP calculations. When we go from ionic equation, the KSP expression, to plugging the numbers in, we forget the exponents.
I don't like calculators.
Are there any questions about that sample? Anything at all?
Just put everything in brackets. Because I multiplied that by 2, and then I squared it, and then I multiplied it by... Alright. I tend to do steps all the time. That's probably why I'm going for my
I'm just trying something.
What do you do?
Pull the button.
I'm just trying something!
Okay.
He knows this.
So it says click here to enable the feature.
No, it doesn't.
Enable the future?
Well, that's just a feature that, like, if I draw two lines and I do this, and then I erase one of them, I've now got two separate lines.
Oh my god.
Do you really?
No, but I didn't enable it, that's why.
You did before.
Actually, I know why, because I have to do it in here. See if I do this, and then erase it.
Oh.
Yes, I do.
Now could you make 3 lines?
If I erase part of it, yes.
Could you make 3 lines?
You get to 1, split it.
Okay, so let's kind of go through this last time. Okay, so everybody's okay with 1.6 instead of the negative 19? Any questions, issues, concerns, worries, urges, yearnings, cravings, desires? Not that I care.
I don't know how you do that thingy.
Go.
Oh. So,
25 degrees.
take a look. Let's take a look at the question. Again, I want to go through in these first few questions, break it down bit by bit, see exactly what the question's asking, how we're going to deal with it. All right, this time, we're going to calculate the solubility. Whoa! What does that mean? Calculating the solubility is the same thing as calculating the molar solubility. Okay, I want to find out how much calcium carbonate will dissolve in water. The only thing I have is the KSP value. So I want to find out calcium carbonate as a whole. How much of that in any liter of water am I going to be able to dissolve? And be expressed in moles per liter. Solubility is moles per liter. So, first thing, ionic equation. Second thing, KSP expression. Go. I think actually if I do this, you just have to do that. No. That's where the touch comes in. Okay, bless you. What do we do now? What do we do now? I've got a KSP value. I need to find the solubility of this. What do we know from the equation? And again, everything starts with the equation. From the balanced equation, ionic equation in this case, what do we know about the two ions? One-to-one ratio. For every mole of calcium I generate, I'm going to generate the equal number of carbonates. So if it's a 1-to-1 ratio, then for every mole of this I dissolve, I'm going to create 1 mole of this and 1 mole of this. So what do we know, 1-to-1 ratio, what do we then know about the values of the calcium and carbonate concentrations? They're equal. We know that no matter what happens, calcium and carbonate are going to be equal. 1 mole of calcium carbonate produces 1 mole of calcium, 1 mole of carbonate. Therefore, concentration of calcium is going to be equal to concentration of carbonate. Yes, sir. Good luck. Leave the camera here.
Oh.
So then what else can we say? If we know that from our KSP expression, what do we now know?
It's square.
KSP is equal to the square of calcium concentration. Or you know what, to make it easier, you can do this step in here. You'd rather put a variable in there? Same thing. Still a big deal. I would probably suggest X because we're going to use variables later on. It'll become important. So now go ahead. Calculate a number. Okay. Okay? Okay. Not that I care because I don't, but. Something in your eye, you okay? Allergies. Sucks. Again, don't care.
Excuse me, is Rizal Rizal?
No, Roselle's on the New York trip.
Okay, thank you.
No problem. So, what do we get?
It does.
Right? Is that my final answer?
No, that's not right.
Is it my final answer?
I got it.
No.
But is that the final answer?
No.
Yes, it is.
Dang it.
Why is it? We have to explain why, though.
It's all the same.
Because 1-to-1 ratios.
So that's your final answer.
So basically what we're saying is, you don't need to put it into this words here. You can go from here, okay, once you actually find the value of calcium or value of X, you can go straight down to there as long as you make, well, because it's 1-to-1 with calcium carbonate, solubility of calcium carbonate's the same number. Is everybody okay with that? Like, you know, this is just to show you where everything comes in. I didn't ask for carbonate concentration. And as I said, if you're using values for X, then you're going to have X is equal to this. So therefore, because calcium is 1-to-1 with calcium carbonate, the solubility of calcium carbonate is equal to. So for marks, which everybody wants to know, 1, 2, 3, 4, 5, 6. Whoa. Got to tell me why the value of X is also equal to the solubility.
Okay.
Okay?
I can't really see the video. It just looks like a giant circle.
Looks like a happy face.
It's so happy face.
Fantastic.
All this is a circle.
Any
That's a
questions?
circle.
Okay, no, I'm not going to do that. Because if we do that, they'll be so messed up.
How long
Everybody okay?
I just heard of the Michael from science. Stupid.
Instead of a screen, you got a maniacal laughter. Because they must move. Yo, what the fuck?
I know.
If you don't know where to start, let me know. We can break the question down.
I know. That's why I drew an arrow. I pulled a mark. I'm sorry.
Man, how do you feel?
No, not the best.
Not bad.
Not well.
Not well. I'm sick, but I'm not well. Martin, you can't figure out your own?
No.
You know what?
He's afraid to pull a Martin.
Put a false number in there.
It's like 10.
At 9.8 times 10 to the negative 43.
Oh my god.
No.
That's it, Martin. Well, there you go, man.
Man alive.
Right. Okay. 6 to the power of -13.
What's your other water bottle?
I got -39, like to the power of -39. Okay, good. I'm not feeling it. I thought my calculator was good.
You know what? Unbelievable. Till the end of the year, we're going to have 2 weeks where we're having a full week of classes.
Oh, God.
Oh, sir.
No, that sucks for you guys. Party.
Can one of those classes be a party?
We don't get chemistry parties.
Yo, Rodney, make love today.
Just being in my presence is part of that.
Oh.
Last time the shower was
Last time the what?
on. The last time the shower was on.
They should run the shower sometimes.
Oh.
Just to be
Just
safe,
to make
you
sure
know?
it works.
Just to make sure it works.
Well, the thing is, I've got no drain down there. Well, there is, but if the drain's at the same level the rest of the floor.
Oh.
Who designed the shower, sir?
Well, they had to put it in afterwards, so the floor was level, so I don't even think I have a drain.
No, there's a drain there. There's like kind of a double where chemistry in the ring. Where's it? Is it under the? It's under the box.
We have a box covered in drain.
It's like just chemicals and water all over the floor.
I feel like, yeah, this is really bad, and like the kids on fire.
It's like after they finish, like, oh wait, this is going to be the chem room.
Right.
That's why I got it, and I'm supposed to be doing it, but I'm supposed to make sure that there's a lip around so the water doesn't spill, because then it becomes a safety hazard. All right, how we doing? Everybody got a number? Mr. Facial! Welcome to chemistry. What an honor. It's a gas. You are on videotape, by the way, because we have students on the New York trip, so we're taping the class for them.
Excellent. Hey guys in New York, say hi to Mr. Champion for me.
All right.
And Miss Smith. Good. That route in, is it open yet? Behind the zoo? How long
It was
has
open
been open?
yesterday, but I didn't know until I drove by.
Okay.
And then I went by because I thought it was open today, and now it's really late, but no, it's still closed.
Once?
They're resurfacing from that intersection at the zoo all the way down Bear Road.
Oh,
And it's going to be, the sign says till May 15th.
thank you.
So, yeah.
I just was in the neighborhood, I thought I'd drop in and say hello and ask you about that route.
You're always welcome in chemistry, you know that.
I like the warp when you bring it up.
Hey, look what appeared. A magic screen.
Maybe
All right.
there. What if it was always there?
Let's go.
And this whole class.
Thank you.
This whole class.
Bonus marks.
No, I'm not high-fiving you.
All right, let's go through this very quickly. Shh. Ionic equation. Oh, is that the final answer, by the way? Everybody got that? So as I said, don't get freaked out if you get like negative, what the heck is that? Because that just means it's slightly soluble. Only a very little bit is able to dissolve. Okay? So these exponents can be really, really high. So, well, actually really small because it's a negative number, so don't worry about that. Okay, so ionic equation first, and we put the KSP expression in. Remember, we're saying that for every liter, that much will dissolve. So that means that the concentration of iron is also going to be that concentration because iron is 1-to-1 with the iron oxide, or iron hydroxide. Okay? Now, that means that hydroxide is going to be 3 times that number. Okay? Then we can plug it in. And again, please don't forget to cube the value. Okay? Excellent. Try that out.
Silver chromate.
I got another box to the box.
So AG, chromate. CrO4 -2 Ag is either 1 or 2. That's going to
CrO4 2 minus or what? Is it 2 minus? CrO4 2.
yeah.
Yeah.
So that's 2 Ag.
I'm gonna take my sweet time. Oh, because you come prepared for class, Martin needs to borrow your stuff?
No, I have my stuff in my bag, so just get it.
That's basically it.
You get this?
He's my calendar on his calculator. I'm sorry to hear that. I'm sorry to hear that too.
See, I'm your calendar as well too.
I don't ask you for
No, that works.
Martin, it's like a point of no return. Stop. Yeah, exactly.
Oh, it's like the time when I ran the table, like.
He keeps going. Just
Yeah.
we didn't even tell him to. Here it is. Here it is. Here it is.
Is it? No, I just want.
Yeah, I screwed up.
How's everybody doing?
Fine. Just like while we're waiting, I'm just gonna keep moving the camera around. So Martin.
X squared times.
Yeah.
It's like the video bro. It's like.
Or 2x squared cubed.
See all these people working?
Yeah, we're done. We're done. We're done.
Yeah.
Matthew did most of the work.
No, I did all the work. It's the usual, you know.
He does no work, so it's okay. He's not doing any work.
He doesn't apply a force over this. Wait, turn around.
That's Martin's graduation day. Oh! He just kissed it goodbye.
And there it goes.
So.
Well, that means you have 1 more year with them. So.
Yay! I can put up with that.
Excitement.
That excitement.
Another year cutting them up.
1 more year.
Only 1 more year.
Future students will know what to pull apart means.
Another year can know what a pull a Martin means.
Just put a picture up.
I'll put it. Yeah, I'll put it up in the corner there. Right in the corner there.
Get a picture.